Hi.
Hello.
Hi.
Hello.
Hello.
Hello there. Wait, so we have a exam this week, right?
Yes, on Thursday.
Okay.
Mm-hmm.
So in-class exam?
In-class exam, yeah.
Is there anything in specific we should study or just everything?
So I guess it's everything up to section 2.1. Yeah, and so, the specifics are on the study guide. Also, it's a good idea. So there's a problem session today. If you can't make the problem session, you should still do the problems because those will help you prepare for the exam as well. So yeah, they're not necessarily going to be cumulative. So it's going to be the stuff that we haven't covered yet, or that we haven't covered on a problem session yet. We have covered it in class. But right, yeah. So, but they're still good to do. Right.
The 2.1 will be in the test?
Yes, it will be. So that was
Awesome. Cool.
Yeah. It was a matrix multiplication and taking transposes. So definitely practice those if you haven't gotten the chance yet. I think they were on the homework as well. Is that right? A little bit on the homework, I think.
Yeah, I practiced doing matrix multiplication properly after our last class. So
Okay. Yeah. It's definitely good to practice because, yeah, it can take some getting used to. I already did that. Okay. Let me get this pulled up. Oh, crap.
Are you reviewing today or?
We're not doing any review. If you have particular questions, I can answer them. But like I said, the problem session would be good review. So I would encourage you go to that if you can. Is this gonna work now? Okay, yeah. Okay, but we have what's going on here? Oh, okay. Right, let me pull this up. Oh, there we go. Okay, almost ready. So we are talking about, let's see, I was gonna talk quickly about these elementary matrices, right? So these were the ones, so last time we talked about finding inverses of matrices and everything, and the way that we do that, which is by taking our matrix A, augmenting with I, and then row reducing. And if it is the case that A is row equivalent to the identity matrix, then what we'll get when we row reduce is the identity matrix. And then on the other side, the part that we augmented with I, we get A inverse, right? And this is how we find the inverse of a matrix for any size matrix, right? Well, it should be square because otherwise we won't have an inverse. But we talked about, or we did not really talk about why this was the case. So the idea is we can express these elementary row operations using what are called elementary matrices.
Yeah, I'm in the Zoom call.
Okay. Here we go. Okay. So, and so what these matrices do when we multiply them, when we multiply by them, so when we multiply a matrix by an elementary matrix, what it does is it applies an elementary row operation. Operation, right? Okay. So we have three elementary row operations, right? So let's look at what those matrices would look like. So if we want to swap two rows, we'll call this E1. This matrix, basically we take the identity matrix and whichever rows we want to swap, say we want to swap rows 1 and 3, we swap the rows of the identity matrix. So I'm going to do the example for a 3 by 3 matrix. So instead of having 1, 0, 0, we replace that with 0, 0, 1. Since the second row is not changing, it stays the same. And then we place the last row is going to be 1, 0, 0. Right? And what this does is it swaps rows 1 and 3, right? And we can check if we multiply E1 by an arbitrary 3 by 3 matrix, so just say it has entries A, B, C, D, E, F, G, H, I. And when you do the multiplication, so you take your first row of E1, that's 0, 0, 1, multiply it by the first column of this matrix, it picks off just the last entry in that column, so it's G. And then the same thing happens with the first row times the second column and the first row times the third column. So we get GHI. So you see the third row has jumped up to the first row. And then the second row times the first column, we get D and then E, F. And then in the last, multiplying the last row by the first column, we get A and then B and then C, right? So it did swap the first and third rows, right? Another thing about this type of matrix, so like a swapping elementary matrix, E1 inverse would be E1. And you can go through and actually compute the inverse using the method that we used before, that we learned last time. You can also just, think about how this works. If you were to swap rows 1 and 3, and then swap them again, you should get the identity, right? You should get the same thing back again. So this is something you can check. We won't do that.
Pardon me.
Mhm.
Is there a reason why you've designated it as E sub 1, or that's just a generic one?
It is, yeah, it's just to have different names for the different types. The one isn't really that important. It's just because it's the first one we're talking about.
Cool. There's no like directory of elementary matrices and each one has a number.
No. Yeah, that sounds terrible. So no. Okay, so that is the first one. That's for swapping. The other two elementary row operations that we have are multiplication by a constant and replacement. So first, let's talk about multiplication by a constant. So multiply by a constant. So this is going to look like essentially a identity matrix, but instead of having a 1, say we want to multiply the second row by a constant k, right? Then we replace the 1 that would appear in our identity matrix with a k, right? So in the second row. So this what this does is it multiplies row 2 by k, right? And we can double check by looking at the matrix multiplication. So E2 times our standard matrix. We would get just A, B, C in the first row. And then in the second row, each time we do the multiplication, we get K times D, K times E, and K times F. And then the last row is G, H, I. Right? Okay. And then also E2 is also invertible. So if we look at E2 inverse, again, you can compute this, but this also makes sense if you just think about it. The matrix that would undo this operation would be the one where we divide by, sorry, that should be a 0. Divide by k, essentially. So we multiply the second row by the constant 1 over k, right? I guess we should specify that constant k not equal to 0, right? Okay. And then the last one is, of course, the most complicated row operation, and this is replacement, right? This is where we take one row and we replace it with that row plus a constant times another row, right? So it looks like, so this is our third elementary row operation. If we wanted to have something where we replace, say, row 2 with row 2 plus k times row 3, we would have this k, which occurs in the second row, third column, and that's going to achieve our replacement. So what this does is it replaces row 2 with row 2 plus k times row 3. Okay, and obviously these are just specific examples, but you can use this sort of setup to get any possible example of an elementary row operation, right? And so we can see what this does to our matrix. And when we do this multiplication, let's start with so if we multiply the second row, so we're sort of starting here, by the first column, we get 0, we get a D plus KG, right? For that first entry in that row. And then when we multiply that second row by the second column of our matrix, we get E plus K times H. And then in the last column, we get F plus K times I, which is what we would have expected out of this, right? That's what we were looking for. And then the other rows do not change. G, H, I. Okay. And again, we can talk about the inverse of this guy. And what that will be is basically we want to undo the addition of that k times row 3. So it would be 1, 0, 0, 0, 1, 0, and we would want minus k there. Right. And for all of these inverses, I'm just telling you what the answers would be, but you could double check by actually computing the inverse, right? We know how to do that for any matrix. So you could just take this elementary matrix and find the inverse. Right? Okay, so in particular, all of these elementary matrices are invertible. So okay. Okay, and that will come up in just a second. So we wanted to, so I believe we stated this theorem last time, and now we can prove it. So this was that A is invertible if and only if, so this double-sided arrow stands for if and only if A is row equivalent to the identity matrix, right? The n by n identity matrix. Okay. Great. So I just wanted to say something about proving this type of statement. I know we've done stuff like this. Why do I always flip these? Okay, this is invertible. There we go. Invertible. Yeah. Right. So proving this type of statement. So we have done something like this before, but I just want to be really clear about what we're doing, like the assumptions we're making, why we're making them, that type of thing. So this if and only if, we can sort of break this down into two statements, right? So it's saying that these two things are equivalent, and that is saying that, so this says two things. So first of all, that if A is invertible, then A is row equivalent to the identity matrix. And the second thing it's saying is that if A is row equivalent to the identity matrix, then A is invertible. Right. So there's two things we need to prove if we want to prove that this is true, right? And so the way that we go about showing this type of statement, so say focusing on this statement, this part 2, what we do is we assume that this is the case, this if statement, we assume that's true, and we have to show that this follows, right? So if we want to prove an if-then statement, we need to assume the if and show that the then must be true, is sort of how we approach this type of thing, right? Okay, so we would need to prove both of these things. Okay, so starting off this proof, we'll start with the first statement. So part 1, right? We assume that A is invertible. Okay. And our goal is to show that A row reduces to the identity matrix, right? Okay, so this is what we're looking to do. Now, what we do know is that, sorry, need to move this over. Okay, so last time we did have a theorem. So by a theorem from last time, if A is invertible, then this equation, ax equals b, has a unique solution. Remember that we even were able to write it down, so that unique solution was A inverse times B, right? Okay, so that's how we know it has a unique solution, because in every case, we can just write it down, right? Okay, so we have this has a unique solution for every B. And what that means is that A has a pivot in every column. Because if A did not have a pivot in every column, then we would have free variables, which would mean that not every time do we get a unique solution. There are some cases where we get infinitely many solutions. Okay. So since A is squared, this also means, I guess that should be somewhere up here. A is n by n. Sorry, that should be in there. Okay, since A is square, what this means is that A also has a pivot in every row, because they're the same number of rows as columns, right? A also has a pivot in every row. Okay, now A has a pivot in every row and every column, and this essentially means that a row reduces to the identity, right? Maybe I'll write this out in words. So this means, therefore, okay. Any questions so far, or this is okay? Okay, so what we've done is we've achieved our goal, right? This was our goal, to show that it row reduces to the identity. We did that. So that means that we've proved statement one. So statement one is done. Now we need to take care of statement two. So the way that we do that is we assume the if, so we assume that a row reduces to the identity, and we want to show that, so I'll use WTS, means want to show that A is invertible. Okay. So we have that A row reduces to the identity. Now we're going to use those elementary matrices that we were talking about before this. So if A row reduces to the identity, then there are a certain number of row operations we apply in order to row reduce it, right? So that means that there exist, okay, so maybe, so there exist elementary matrices. We'll just label them E1, E2, up to EK, right? Such that if we take A and we apply the matrices one at a time, so we'll first apply E1 by multiplying by E1, and then apply E2, and then keep on going. And last we'll apply EK. And after applying all of these, we know that we should get the identity. There are some matrices that we can apply in a certain order that will give us the identity. Okay, so we have this. And like we were saying, when we were talking about these elementary matrices, each of these, EI, each elementary matrix is invertible. And we also know that the product of two invertible matrices is invertible. So we can just keep multiplying. So if the product of two invertible matrices is invertible, then also the product of three invertible matrices is invertible, and so on. So the product of any number of invertible matrices is in fact invertible. So this means, so this entire product, EK up to E1, is invertible. And not only that, we know that its inverse will be the product of the inverses of each of the individual matrices, but now that's in the opposite order, right? So we have to change the order. So E1 inverse times E2 inverse up to EK inverse. And this is using the fact that AB inverse equals B inverse times A inverse. We just use this fact repeatedly, right? And we'll end up with this. Okay. So what we have now is if we look at this guy up here this statement right here, I'm just going to take that, copy it down. So we know that EK times E1 up to E1 times A equals the identity. And then we can take this thing and multiply on the left. So remember, when we multiply in a matrix equation by something, we have to multiply by the same thing on the same side, right? So it matters which side we multiply by. So I'm going to take this thing, I'm going to multiply on the left by E1 inverse times E2 inverse up to EK inverse on the left. So we get this thing, and then we get E1 inverse times E2 inverse up to EK inverse times the identity, right? Okay, now when we multiply this out, we can group these so that we first get EK inverse times EK, right? And those will go away. And then we group EK minus 1 inverse times EK minus 1. So essentially we get all of this collapsing. So this entire thing will collapse to the identity times A, right? And then on the left-hand side, we get this product. Okay, so essentially we get A is equal to this product of elementary matrices. Right? Okay, so the reason this is important, why does this matter? It's because now we've got A written as a product of invertible matrices. So A is equal to this product, which means that A must be invertible. We know this product is invertible and A is equal to it. Therefore, A must be invertible. Right? Okay. And that's what we were looking for, right? That's what we wanted to show, that A is invertible. So technically we're done, but we can say a little bit more. So why not? Let's do that. So furthermore, if we look at this guy, we had, so this was this green statement up here. I'm just going to copy it down. So EK up to E2 times E1 times A equals the identity, right? That thing times A equals the identity, and A times, if we multiply by the same thing, but on the other side, E2 times E1, we get, so here I'm using the fact that I'm going to replace A with this right here. So let me just plug that in for A. We get E1 inverse times E2 inverse, EK inverse, and then that'll be multiplied by EK up to E1. So again, this all just simplifies down to the identity. And what this shows is that this product of EK up to E1 is the inverse of A. So therefore, A inverse equals EK times EK minus 1 all the way down to E1. Okay, so not only is A invertible, we can write down what the inverse is. And we get it by just multiplying together all of the elementary matrices that row reduce A to the identity, right? Okay, and so this actually shows us, so why this method works of finding inverses. So this method where we take A and augment with the identity matrix. So knowing that elementary matrices, right, they don't change, they are applying an elementary matrix is like applying an elementary row operation. So this should be definitely equivalent to E1 times A and E1 times I. So this is just applying a row operation. Those things should be equivalent. And then you can apply another one, right? And then just keep going, right? Until you've applied all of the row operations that will give you A being the identity. So EK up to this guy. See that this is the identity, right? So we get the identity. And then on the left-hand side, that's exactly that thing that we said was A inverse, right? That we just proved would be A inverse. And that's why that's what we get on the right-hand side when we do these row operations. That's why that gives us A inverse. Okay. Hopefully that makes sense. Okay. How are we doing on time?
Can we do an example like of this?
An example of like finding an inverse.
Yeah.
Okay. Let me see if I can pull one up real quick. If I just make one up, it's somewhat likely that it will not be invertible. So I just want to make sure it will actually be invertible. Maybe I can find one from the textbook. Okay. Okay. Let's see. I'll try. I'll try to make one up. So example. Okay. Okay, I think that'll work. I can't do this in my head, but okay. We're gonna check that this is okay, do -2. Yeah, okay, this should be invertible. Okay, so we want to find A inverse. To do that, we augment A by the identity matrix, so it will be 1, 2, 1, 0, 1, minus 1, 4, 2, 0. Like that. And so we want to row reduce this guy. So first, let's clear the this column, so there's stuff below that first pivot that we want in the first column. So we can take row 3, replace with row 3 minus row 1, right? So if we do that, we'll get 0 here. Row 3 minus row 1, that's a 0. 0 minus 4 will give us -4. And then 0 minus 1 would give us -1. 0 minus 0 is 0. And lastly, we get 1 minus 0. So that's just 1. Okay. And then at the same time, I know I told you not to do more than one row operation at a time, but I'm cheating just to make this a little bit faster. But we'll take row 2 goes to row 2 minus 2 times row 1. And that will eliminate the 2 in that first column. So we'll get 0 here. We'll get 1 minus 0. So that stays as 1. We will get 2 minus 8. So -6. 0 minus 2 is -2. Here we have 1 minus 0, so 1, 0 minus 0 is 0.
So this might be an odd way to think of it, but is it like you start out with the identity matrix as your blank canvas, and as you do row operations, it's like creating a pathway. It's telling you how you got from A to I3. Like, it's like sort of like you see that -2 and you know that like you subtracted 2 row 1
Right.
from row 2.
Yeah, it's sort of keeping track of those things. Yeah, exactly. Yeah, and so then like when you put it all together, it is like the process of row reducing that gives you that, right? And it's sort of keeping track of all of those things, which is the same thing as taking those elementary matrices and multiplying them all together.
Cool.
Yeah, so it is. Yeah, it's pretty cool. Okay, so next we want to clear this -1 so we can take row 3 and add row 2. So, okay, just to be clear, this is row 3 replaced with row 3 plus row 2. And so we get 0, 0. Let's fill in this. We get -4 plus -6, so this is -10. And adding those together, we get -3, 1, and 1. Right? And then let's see, what's the best way of going about doing this? So we'll just multiply row 3 by -1/10 to get a 1 there. So we'll get 1, we'll get 3/10, 1, -1/10, -1/10. Okay, and then the rest of this will probably be somewhat messy because now we'll have fractions. But let's see, we can take, so we want to clear now these two numbers in the column above that last pivot. So we get row 2 replaced with row 2 plus 6 times row 3. That'll cancel that -6. And we'll get, let's see, 0. Right. This is still 1, 3/10, -1/10, -1/10. And let's see, 6 times, yeah, this is not fun. Okay. 6 times 3, so we get 18/10 minus 2, so that's 20/10. So -2/10, so -1/5. And then we get -6/10 plus 1, which would give us 4/10, so 2/5. And then -6/10 plus 0, so -3/5. Okay, that's that row. And then at the same time, I'm going to do row 1 replaced with, let's see, row 1 minus 4 times row 3. And that will give us a 0 here. And then we have to figure out all the other stuff. So it would be -12/10 plus 1, which would be -2/10, so -1/5. We get 4/10 plus 0. Yeah, so just 2/5. And again, 4/10, again, plus 0, so 2/5 there too. Okay, and hopefully no mistakes have been made. But this would be your inverse. So we would get a inverse is just this stuff on the right, -1/5, 2/5, 2/5. Honestly, if we want to clean this up, we can pull out maybe a 1/5 or 1/10. Right, and then we get -2, 4, 4, -2, 4, -6, and 3, -1, -1. That would be our answer. Okay. So, I would say, especially when you're doing this type of problem, it's important to remember the sort of order that you want to go in when you're doing your row operations. so that you don't do more work than necessary. So sometimes when you're doing row operations, you can sort of like move in one direction and then move backwards, and then you're doing more work than you really need to. So remember that we have that algorithm that tells us what order to go in. So the first thing you want to do is create your pivots. So you want to start here, you want to clear everything underneath it. Then you move to the next row, or sorry, next column, right? So here we found our next pivot, we clear everything underneath it. And then we get our 3 pivots here, like that. And then we clear everything above it. So then we start to clear the columns above those pivots. So you go forward and then backwards, right? Okay. Right, so that finishes up that section. This was, I forget which section this was, 2.3, I think. And then we get to move, oh, sorry, that would be 2.2. So we're now moving on, sorry, to section 2.3. Yeah.
Sorry, I have a quick question for the order of row operations.
Mhm.
Is there a specific place when you should make sure that your pivots are 1? Because I think the book says to do it in between going forwards and going backwards. But I found sometimes that for clearing above the pivots, it's more convenient to leave them as is.
Yeah, yeah. So I think it does depend on the problem. It's not strictly necessary that you turn them all into ones. Sometimes it is easier to leave it as that constant and then clear, or then, adjust by a constant. So yeah, sometimes it can be the case, like when we divided by 1/10, negative 1/10, in this step right here, we all of a sudden got a bunch of fractions, and then that created fractions in all of the other rows, right? So sometimes you want to avoid doing that before absolutely necessary, right? Because fractions are a lot more frustrating to deal with. Yeah, it's pretty terrible, I know. Okay. Right, so that's something to keep in mind, yeah. Right. Okay. So this next section is on, well, it's called characterizations of invertible matrices. And essentially, we're just talking about this one big theorem that's called the invertible matrix theorem, right? Okay. So before we start like listing all of the equivalent statements in that theorem, let's just mention something about notation. So we know that given a matrix A, and in this section, we're always talking about n by n matrices, but given any size matrix, actually, we have an associated linear transformation. Right, we learned about this. And it's defined by just taking A, that matrix, and multiplying it by your variable x, right? Okay. Now, another way of expressing this linear transformation, another way of expressing is going to be this. So taking your variable x and mapping it to the matrix A times x. So this arrow, notice there's this like backstop on it, right? So there's a line, arrow, and then this is your image of x, right? So this, you can read this arrow as saying maps to. So x maps to A times x, right? In this encodes all of the information you need about that linear transformation. It tells you where your variable is sent to, right? Okay, so this is just like a more compact way of expressing this same linear transformation. So it's the linear transformation that is associated with the matrix A, right? Okay, and so this is how they write it in the textbook. So I just wanted you to be aware of that notation, but it's expressing this associated linear transformation just in a different way. Okay, so once we have that out of the way, we can now write down all of these equivalent statements that are in the invertible matrix theorem. So this is about, like I said, we're talking about n by n matrices. So the invertible matrix theorem, I might abbreviate this IMT. Okay. So say we have an n by n matrix. Then we have all of these equivalent statements about this n by n matrix A. And a lot of this is putting together things that we've already talked about, things that, like ideas that we've already talked about. And it's putting them all into one big giant theorem, right? And this will actually even get larger as we learn more concepts. But so far we have, I think, how many are there? 4, 8, 12 things in this list, okay? So the first statement, remember all of these are equivalent. So the first statement is that A is invertible as a matrix, so it has an inverse. The second, which we just proved was equivalent to the first, is that A row reduces to the identity, right? We just talked about that. Next, A has n pivot positions. Okay. AX equals 0 has only the trivial solution. Okay, remember that was equivalent to the linear transformation, the associated linear transformation being 1-to-1, right? So we showed that a while ago. This is equivalent to saying that the columns of A are linearly independent. Okay. And that is also equivalent to saying that the linear transformation associated with A, so remember we can use this notation to denote that linear transformation. So this is 1-to-1. So G, the matrix equation AX equals B has at least one solution. For every B in Rn. Okay.
Do you also say that AX equals B has exactly one solution for every B in Rn?
Yeah, that's also true.
Cool.
Yeah. Right. So there's so many ways of like saying each one of these things, but yeah, I'm just gonna try and be consistent with the textbook for this, especially for the like numbering of these things. But yeah, there are even more ways that we could express this as well. Okay, so we have up to this. This is equivalent to saying that the columns of A span Rn. And that the linear transformation that sends x to A times x is onto as well as 1-to-1, right? Hi, let's put this on the next page. Okay. J, so there exists a matrix C such that, let me make sure this is actually, okay, C such that C times A equals I, and K, which is similar, there exists a matrix D such that D times A, so multiplication on the, on the right instead. So A times D equals I. And lastly, A transpose is invertible. Okay, so like I said, a lot of these things we have talked about already. These are sort of ideas that we've already talked about. We've proved a lot of the equivalences of these different things, not all of them, right? But quite a few of them. So for instance, let me just move this guy up. Yeah. Items D, E, and F are about being 1-to-1. So D, that A times X equals 0 has only the trivial solution. We proved that that was equivalent to F, to the linear transformation being 1-to-1, right? And also the fact that if the columns are linearly independent, the columns of A are linearly independent, then the matrix, or not the matrix, then the linear transformation is 1-to-1. So D is equivalent to E is equivalent to the F, and this has to do with the linear transformation being 1-to-1. Okay. And then also, let's see, G, H, and I are also equivalent, and they have to do with the linear transformation being onto, right? So linear transformation being onto. So G says that this equation AX equals B has at least one solution for every B. H says that whoa, sorry about that. Okay, undo. There we go. Let's see. H says that the columns of A span R. That was equivalent to being not 1-to-1. That was equivalent to being onto. And then of course, I just says that the linear transformation is onto, right?
Just a question.
Yes.
So then if AX, the linear transformation, if it's both like, it's saying that it's both onto and one-to-one.
Both onto and one-to-one, yes.
So wouldn't that mean like every vector B in Rn would be hit by exactly one vector X in the domain?
Yeah, yeah. So I mean, we can replace this at least one with exactly one, really. Right. I'm really just writing it this way because they do so in the textbook, but I don't necessarily agree with it. So if you want to just replace that with exactly one, that's fine with me. It
I
is.
think it's, oh,
true.
sorry.
Go ahead.
I think it's because the textbook talks about like existence and uniqueness a lot as different
Right.
concepts. So they're
Yeah,
trying to keep them separate. But
that may be.
yeah,
Yes. Yeah. So
I didn't know.
yeah. Right. So there are, of course, all these different ways of thinking about it, but it is true. It will be both one-to-one and onto, right? Okay. So, right. These are things that we've talked about before. Other things that we've already shown are that A, I know like it's not totally visible now. So A is equivalent to L. That's that if A is invertible, then A transpose is invertible. This just comes from the properties of transpose, right? So A is equivalent to L because, by the way, this is shorthand for because A transpose inverse was A inverse transpose, right? So we showed that. We showed that F was equivalent to D. Oh, we already listed that one, so that's not necessary. We showed that A was equivalent to B, right? We just proved that. And we also showed that A was equivalent to G last time, right? That was having to do with writing down the unique solution by using the inverse of A, right? That X equals A inverse times B. Okay, so there's probably more that we've already shown. I'm not going to go through like sort of the entire proof of the entire theorem because it mostly involves keeping track of what you've already proved and what you need to prove and using like some little proof techniques that are, I don't know, not necessary, I feel. But it's good to see how these different statements relate to one another so that you can move from one to the other. Yeah, but that's what I have to say about that. There is one thing I did want to point out in here, which is these statements J and K, right? So J and K right here. These essentially say that when we're looking for an inverse of A and we find, say, like a left inverse, so we find a matrix that we multiply A by on the left and we get the identity, then A is invertible, so long as A is square. It is actually really important that A is square. But if you have A is square and you find one matrix that you multiply by on the left and get the identity, then you have your inverse already. You don't have to check the other multiplication. So that's useful to know, right? So let me write that down. So okay, cool. Where are we here? So the fact that A is equivalent to J slash K this says that we only need to check one of the following equations. So if we have A times B equals I and B times A equals I tells us that B is equal to A inverse, we only need one of these to conclude that B is A inverse. Okay, but very important, important is that A is square, because this would not be the case if A was not square. Okay, so let's see. I'm going to go ahead and prove this because we haven't talked about this particular thing. So proof, we're going to do, so I'm going to use the this condition K and the proof for the fact that, so I want to show that K is equivalent to A, and the proof that J is equivalent to A is essentially the same, right? Okay, so what we want to do is first suppose, remember this is an if and only if statement, so we'll suppose that A is invertible, and we want to show that that we get this, that there exists a matrix D such that A times D equals I. But that basically comes from the fact that A times A inverse equals I, right? So A is invertible, we get this, so take D to be A inverse, right? So that one implication is pretty straightforward. So that one wasn't hard. We're done with the first one. Now we suppose that A times D equals I, and now our goal is to show that A is invertible, right? Okay. So for any B, we have that, well, B, if we take B times the identity, that's just going to be B, right? So we get this. B is equal to the identity times B, but we can replace that identity with this A times D, right? Because you know A times D is equal to the identity. So A times D times B, right? That's fine. And then we can group this. So this is equal to A times D times B equals B, right? So what this says is if T is the associated linear transformation, so if T is given by this, then what this says, so I'm going to put a star next to this. So what this statement star says that T of X equals B has a solution for every B. Namely, we take X to be that matrix D times B. Okay, so what that means in terms of T is that T is onto, right? If this has a solution for every B, this is the definition of what it means for T to be onto. So T is onto. Okay.
Yeah.
Yeah.
I don't really understand. I'm sorry. Like, I can tell that the star statement is true,
Mhm.
but I don't get how it shows that Tx equals b has a solution for every b.
Okay, so if you're looking at Tx equals b, you want to know if this has a solution. Well, this side we know from the definition is a times x. So you really want to solve ax equals b, right? Okay, but if you let x equal d times b, then a, you plug in d times b, and then we simplify. That's just the identity times b, so this is b. So x equals d times b is a solution. And we can do this for any b, right? So this always has a solution. Does that make sense?
A little. I guess I just need to go back and look over linear transformations some more. Thank you.
Okay. Yeah, no problem. Okay, so we have this so far. So what we have concluded is that T is onto, okay? And what that means is that the matrix A has a pivot in every row. So if we look back at sort of the equivalent statements that we had about functions that are onto, or linear transformations that are onto, this means that A has a pivot in every row, right? Okay, and then, so remember that if A did not have a pivot in every row, then we could possibly get an inconsistent system for some vectors B, right? So that was why T being onto meant that A had to have a pivot in every row, right? Okay, so pivot in every row. That means that A has n pivots, right? Because there are n rows, so n pivots. And since A is square, well, not even that. So A has n pivots, and we know that this first, sorry, going back up here, that A is equivalent to C already. If A has n pivot positions, then A is invertible. So we're using that equivalence to make this conclusion. A has n pivots, so A is invertible.
So this whole thing is trying to show that A is invertible if K is true.
Yes, exactly. Yeah.
Oh, I guess it's hard for me because like when I read that AD equals the identity matrix, then that's automatically telling me that A is invertible because that's how the definition of invertibility works.
Right. So it's half of the definition of invertibility, right? Because A times D equals the identity. You would also need to check that D times A equals the identity, right? Usually.
Oh, I thought you said that we didn't have to check that. I'm sorry. Now I'm confused.
Okay, yeah, that's what this is saying. So we are proving this to be able to say that when we have one side of that, so when we have A times D equals I, we don't need to check. So if this is true, we don't need to check D times A equals I. And it's because of this, so we're going through and proving that that's the case first.
I'm sorry, I still don't understand.
Okay. Okay, so what I was saying up here is that, so by the, let me put it this way. So the definition of invertibility is that if you have A times B equals I and B times A equals I, then B is A inverse, right? That's our inverse right there of A.
Oh, okay, so you're using the matrix from K, and then you've proven that if K is true, then A is also true. And then you can go ahead and say that since you know A is true, then the matrix D is the inverse.
Yeah, exactly, yeah.
So you're
Okay.
simply saying that you don't have to check both of them, just
Yes, yeah, that's, yeah, in the end, that's what we get. Because by the definition, we do have to check both of them. But now we know that if we have a square matrix, that we can go ahead and conclude that by having one side or one of these equations. Yeah. Okay, so how are we doing on time? We have 4 minutes left. Okay, so I guess I'll just end with this. We haven't quite finished with this section, so we'll finish that up on the next, right, we have the exam next time, so it'll be next week. But the idea behind the invertible matrix theorem, let me make this clear. So idea behind the invertible matrix theorem. It's that there are two types of square matrices. So we can sort of split them down the middle, right? So there are square matrices, and one type is, square matrices. So on one side, we have the invertible matrices, and on the other side, we have non-invertible. And they're like two different camps, right? And for the invertible matrices, all the statements of the invertible matrix theorem are true, right? We know that every single one of them holds true. For the non-invertible matrices, we know that all the statements of the invertible matrix theorem are false, right? Okay, so, and your matrix, your square matrix will fall into one of these two categories, and then you'll have all of these statements that you know about that matrix. They'll either be all of the statements that we have from the invertible matrix theorem, or they're the opposites of those. So for instance, if we have a non-invertible matrix, sorry, I'm going to scroll all the way back up here, then for any, we know that, for instance, this part H, we know that the columns of A do not span Rn. We know that the linear transformation is not onto like all of these statements, but the opposite, right? Okay. So that, I guess we'll just end there. Next time I'm going to do a couple of examples using the invertible matrix theorem just so you can see how to apply it. And then we'll finish up with talking about invertible linear transformations. Yeah.
thank you.
Okay. And so I do have office hours today. I think that's the last time I have office hours before the exam. So feel free to
So
drop.
the
What's
exam
a quiz
will be,
today?
sorry.
What's that?
So the exam